And thank you for that. Following this coming presentation, there will be a 5-minute break. We invite you to get coffee, pastries, some fruit over, and we're looking forward to that. So after this presentation, again, the break, and coming up, this is the HISA Technology and Data Integration panel. Lisa Lazarus, Steve Keech, both of HISA, will be presenting.
Good morning, everyone. I just want to start by thanking Grayson for this opportunity and for holding this summit every year. It's incredibly informative and important, and no matter how much better we may be, as Dr. Parkin explained, we still need to continue to do all we can to, I think, to work together and improve. So I wanted to just introduce Steve Keech and what our presentation is going to focus on today. You heard earlier this morning how the EID was really the start of everything, of sort of all of this research that we've had around data relating to horse injuries and fatalities. And that gave us, the foundation on which to think about how we might use the HISA data and how we might actually, build our portal in a way that is helpful and contributory and really provides tools primarily for our regulatory veterinarians. Jockey Club and Dr. Parkin were absolutely, sort of visionaries that many years ago, and we're lucky to have that to sort of build on. Steve Keech, the man to my left, he was hired by the HISA board. Actually, he predates me at HISA to essentially build the HISA portal. He was handed a blank piece of paper. Actually, he was handed probably the statute and told, this is what we need to do. Build it. And, I would say we've come a long way since the early days when we were just struggling to get covered persons registered. And now we're able to actually try to take advantage of the 7 million or so veterinary records that we have in our system in order to really bring more information to the industry and, contribute to reducing the risks of equine injuries and fatalities. I think you'll enjoy hearing about how that risk, how basically our system and ultimately our risk model was constructed, both the architecture and how it was delivered. We're going to start by me showing the finished product of kind of one of the tools that we provide to the regulatory veterinarians today to really assist them with their work on the race course. And then we're going to work backwards, and Steve is going to explain to you how it was built. I'm going to hang around to decode him in case he gets too technical and people's eyes start to glaze over. But he's usually pretty good at providing analogies and explaining what's going on. So if we can just roll that video. Just advance the slide? They're here. Okay, great. There we go.
HISA Horse Insight is a powerful tool that allows regulatory veterinarians to take a look at a horse's history right there in one place. There's so much information on this horse history graph, including all these event types. You can hover over any of these event types on the timeline and get detailed information about each one. You can look at IAs, injuries featuring limb and structure, races, scratches, treatments, veterinarian lists, and workouts. Hover over any of these, such as a race, vets list. You can find out the reason for the vets list, workouts, IAs, races, etc., and get more details. A green triangle with limb and structure in it will give you details about a treatment featuring limb and structure. If we go over to the sidebar, you'll find information about furlongs as of the date that you generate the graph. HISA Horse Insight has so many different views that you can open up to get detailed information about different things, such as races. In this view, you can see all this information about all these past races, including the HISA check, workouts, layoffs, etc. The race card view allows you to look at a bunch of different horses all in the same race with their horse history on individual timelines. You can narrow in on a particular horse by clicking on that horse. The remaining horses will fade into the background and you can just focus on that one timeline. You scroll down, we have the quick stats on every horse in the race that you've selected to view. And if you click anywhere on that quick stat card, it will open up a horse info card with AI generated information about past performances and health information. To learn more about an individual horse's history, you can just click here on any of these horses to view the history graph. So that is just an overview of some of the highlights of HISA Horse Insight.
Is that, oh, no, that's on. Okay, good. Thanks everyone for giving me a chance to see all the great work that the folks at HISA have done. We're going to walk you through HISA Check. So that's our risk model. And we've gotten a lot of questions from some of the folks who've been interacting with it. It's like, well, how does it work? And so this will, we'll try to quickly run through how HISA works, how HISA Check works, both from getting the data in, what's behind the models, and what's the governance around it, because you'll start to find that that is the most important thing is what do you do with it after you got it? So does green mean go? Yep. Okay, so here's the HISA Check walkthrough. We've already talked about this a lot, so I'll just quickly try to blow through it. Essentially, horse racing has this great thing when you're looking at machine learning, which is we have the curse of dimensionality and the scourge of scarcity. And what that means is we got a lot of data. We started collecting data back 1896 was the first PP that I could find. I don't know, maybe I'm wrong, maybe it even goes back even farther, and we take a look at all the data we have on past performances, races, breeding, et cetera. There's a lot of data out there, and it extends, when you look at that over time, the number of horses, you got this massive data set. And I think the discussion we had earlier this morning on the EID just basically informs that, yes, there are billions of data points. But if you're trying to look for just a small sort of needle in that massive haystack, it gets a little tough because you're just trying to find something really, really rare. And there's that classic thing, if I just assume that no horse will ever get injured, my model can still look like 99.9% accurate, but that's not good enough. So that's our first kind of takeaway from this. Make sure I didn't miss anything exciting. Oh yeah, if you want to sound really cool with your math friends, you can say we have sparse high dimensionality, just in case. Go. Next. It's a good thing I'm the IT guy. Oh, there we go. Here we are, jargon and slang. That's another thing we have in going for us in our data set. We have a significant number of ways that we say stuff, especially when we're humans. The little graphic there shows you money's the worst one in the world for all kinds of different slang. And we're getting this ingest of all of this data from people who are going to key stuff in, and it's the unstructured data that gives us most of our really good, the new information that we're looking for. As an example, if you just take a look at when people are trying to enter in drugs and stuff, ACE promazine, there are 274 unique ways that people have entered ACE promazine into the system. There are 401 unique ways that people have entered, I'm going to blow this one, phenylbutazone. Bute. Got it. That's one in a row, baby. So you can see how this level of variation is going to make it pretty tough. Don't forget what I just talked about, which is that the curse of dimensionality. So I got all of these variables, and guess what? Inside of each one of those variables, there's 401 different ways I could say the variable. Okay, so I know there's a whole bunch of people screaming in their head, standards, standards, well, oh my God, just enforce standards. Well, absolutely, except standards take a long time to implement. They're costly from a standpoint of maintaining them. They're slow to implement, and we don't got a lot of time. So I know it's tough to see, but if you look at the little roboties down the bottom corner there, they are announcing the fact that they've agreed to the size of the font that they're going to use in their press releases, so they're pretty excited. It only took them a year. On to the next one. So what are we doing about it to try to deal with this sort of chaos of stuff coming in? We're using natural language processing. Essentially what it does, and if you look at the little robot guy, he does a pretty good job explaining it to you. I'm going to take all of those different ways that people say ACE. I'm going to stick them in, I'm going to chop them up, I'm going to put them in a blender, and then I'm going to spit out a standard. So you're essentially teaching the machine learning algorithm how to read human. So we have one of those for each of the fields that people start filling in, which is free flow text. You want the free flow text because it lets people tell you stuff they may not tell you if you just had a drop down. So that's what we have on that one, and as you can see there, the example, these are all, not all 290 some, but you'll see how it takes all of that stuff and basically says, hey, this horse had ACE. So now we can use that as a factor. On to the next one. So this one may seem a little like, oh man, the transition here is poor. Oh well, sorry about that. I only have so much time. But it comes down to people think in categories. And when you're building a machine learning system, the first thing you really have to think about is thinking about thinking. I know that sounds like something deep you might get from your drunk friends around a campfire, but that really is what you got to spend a lot of time doing. So because we have these categories, you know, you go outside, you don't think, oh my God, it's 83.9 degrees and it's this kind of humidity. You go, man, it's hot. That's it. That's what you got. And because of that, people will both use these categories. Even if you're entering a number, in the back of your head, you're going to have a little thing that goes, yeah, that's hot. And so instead of saying it's 80 degrees, you may go 81. So your tendency to categorize is even going to hurt when you're just trying to get a numeric input. And when you get the outputs, you're also going to categorize it in your head. You're just naturally going to do that. Sorry, it's how we deal with stuff as humans. So, and it doesn't help that these categories change over time, right? Like the little sign says, right? Rich is rich. Yeah, but $1 million isn't what it used to be, right? So it's that whole thing of, hey, fast is fast. But maybe not as fast. And so what are we going to do about that? This idea that we want stuff in categories because that's how we use things as a human. Things change over time. Help me out. I got all this raw data, billions of pieces. Well, I'm going to use what's called feature engineering. Don't worry, as it says on the little chart there, that equation's not going to be on the exam, so you're good. You don't have to memorize it. The feature engineering part, what it does, it takes all of our data that's coming in, and then it applies some logic to it so that you can get something which you can use, over time, and you can even use it for people in a conversation. That particular example there is our feature engineering algorithm for drop-in class, which takes into account the type of race, the purse, and the claiming price if it's a claiming race. And so what it means is when I say, hey, a horse dropped in class, and you say a horse dropped in class, we can both say, hey, this horse was a 6, went from a 6 to a 5. But yet you might have a different thing in your head when you say, hey, it's a drop in class. And so this standardizes this as we can look at it over time. For those who maybe have some little more specific questions, is we use when you look at those parameters there, If it's a regular claiming race or the regular price, you're always going to generate the same number. But if you fall outside of the 2 standard deviations on either side of the mean, meaning you're like, it's a really, really cheap race, or it's a really, really expensive race, or it has a really, really small purse, or it has a really, really big purse, we're going to move you around a little. So that's data ingest. Now, at this point, I'm going to jump into the model. Our model is basically 4 models. We have 3 individual models. Each one of them provides their input to an ensemble, to an overseer model, and the solution type that we use is called, it's an ensemble. This over here, scrolling by, is all of the are all of the features of the model. When we're communicating in the press and stuff, we use risk factors. It's okay, somewhere this will be posted. You don't have to memorize them, but it was more just to get a sense of, there's a lot of different stuff in there, and please cast your mind back to the fact that we have that whole class drop thing, is the class drop is one of those lines. So a bunch of information went into generating each one of these. So they're features. That's the term of art in machine learning. Wanted to sort of have that scroll back and forth, basically, because there's a lot of people when they take a look at HISA checks and the outputs, et cetera, like, wow, so, like, do you look at this? Yes, we do, whatever this is. However, we may not look at it the way you think we're looking at it. You may not, it may not have as big an impact, or we may have run a feature engineering across it. And I neglected to say, which I should have mentioned, is you feature engineer to reduce the noise and heighten the signal. That's the whole purpose of feature engineering. Okay, what do I make sure I got everything exciting there. This guy. So the other thing we run into a lot of is people say, well, what are the weights? Because not every feature is equally weighted. And you go, yeah, okay, I got it. And we've had people say, well, I want to be able to adjust the weights. We let the model adjust the weights. And we use this thing called primary component analysis. I'm sure you probably use that every day in your job. But this component, what it does is it looks at how much variability of the signal that we're looking for is determined by a particular risk factor or a particular feature that we have. And what we do is we take a look at this and say, hey, if you're not in the 90% of features that help inform us on our output, maybe we're not going to listen to you that much. We're not going to get rid of you. We may not listen that much. However, if you're the number 1 or the number 2 or all the way up to probably 16 or 17 is what we're generally finding on feature sets, you get most of the variability of the variables picked up. So, okay, so this equation is on the exam, so don't forget that you got to take that. Our first model is a point-in-time model, which uses logistic regression. And as all of you looking at that can see, right, you've got 1 over 1 plus an exponential equation. Okay, here's what that really means for you, is you get this layer down the bottom, you'll get a line up to the top, and you'll get another layer across the top. So this group down the bottom, let's call them low-risk horses, and we'll call this group at the top called high-risk horses. And this line are the ones that don't neatly fit into the 2 categories. And so what this particular thing does is says, hey, let me take a look at the risk vector, the risk factors at a particular point in time, and see, are you in the bottom group or this top group, or are you somewhere in the middle? And then the model, using things like the PCA, will figure out where do I want to put the line of the middle. Like if you're, I don't know, 0.75, do I call you high risk? Do I call you low risk? How does that work when I take a look at my predictions? And I learn by taking a look at the mistakes I made, and so I start changing my model, and I end up with this thing that says, hey, the model will figure out where it wants to put this middle piece. So That's our friend, logistic regression, and it's a point in time. This next little guy is our time series. And we use what's called long short-term memory, which is, sounds a little like something that happens after you've been drinking all night, but it's a series, basically it's a time series of those risk vectors that we had in the first model. So every day we calculate those risk vectors, and then we bang them together into a great big matrix or spreadsheet thing, whatever analogy works for you, and then you take that and you jam it through this thing. Now, it's a regression model, which means it, in both of the cases with regression models, it tries and tries different weights of different parameters until you finally end up with something that's accurate. And it uses, the fancy term is a loss function. If anyone here has done simple least squared regression, then you know all you're really doing is bending the rubber ruler until the error is minimized. And so that's what we're doing here. We're just doing a little more complicated. A couple things to pick up on that. I may need my glasses for this. Hold on. Input gate, forget gate, and you'll notice the sigma function. So first of all, I really like the forget gate. As my wife likes to say, my forget gate is turned up to maximum all the time. But the forget gate says, hey, I don't want to hear about stuff that happened a year ago. Or maybe the forget gate says, yeah, I think I want to hear about the stuff that happened a year ago. The input gate tells you, hey, this is the stuff that happened yesterday. I want to know about it. Or, don't tell me about yesterday. It doesn't matter. And so each of those parameters are layered against all of those features that you saw scrolling by on the screen in order to say, hey, this particular thing, class drop, say, just because I'm going to focus on that one, is this happened a year ago. Is it important or not? We're going to let the model and the regression and the math tell us, does it actually help improve the accuracy of the model? The other thing is you'll notice that it's got a sigmoid and it's got a tan H in there, and the reason for putting those in or highlighting them is they work the way your brain works. So your brain, your dendrites or neurons or whatever, you'll see it get a bunch of input just coming along, and then when enough inputs hit your brain, it fires and you do something like, I grab this coffee cup and it's hot, I'm going to let it go. But if it's not that hot, I won't let it go. And so this works a lot like a neuron to be able to say, hey, here's a whole bunch of my inputs, I'm getting stuff, I think there's something there, and then when it builds up to enough weight, it'll go, yep, this is something I should pay attention to. And then you take a look at, hey, I'm taking a look at what happened in the past and what happened in the future, and I've got this thing here. Okay, on to the next one. K-means. This one is very different than the other two. Number one is point in time. Number two, time series. So let me take a look at what's going on over a period of time. Number three is, hey, these are horses that are really similar to one another. Maybe it's similar by age, maybe it's similar by number of starts, maybe it's similar by the race that they're about to run or the race they just ran. So we're going to build these similar groups of horses. We're then going to figure out what sort of outcome of the horses do we want to get to. So we'll take a look at, and I totally forgot, I blew right through this at the start, my bad, is we've expanded what we call, we don't just look for death, we look for what's called bad outcomes. And a bad outcome will include, injury, DNF, injury, vet list, layoff, retirement. So, and death. No, death is always there. So we would take a look at these groups with these particular kinds of outcomes in them, and then we would say, all right, I have a horse, here are my groups. Which group does this horse most look like? And how close is it? And so it's a way of sort of taking that piece. So if I look at all three of those things in your head as a human, you're like, okay, well, what's going on today with the horse? what's this horse's past history look like? And is this horse like that other horse, which I'm a little bit worried about? So those are the 3 different kinds of models that go together to basically spit out, each one of them spits out their own belief about a horse's risk. And then you get to the last one, and there's nothing too exciting about this. This is a standard neural net that just looks at patterns. So you basically give it a bunch of inputs, you show it what the output should be, and it figures out what patterns it wants to look for. And so it takes point in time, time series, and similarity, and then pumps out is this horse at a greater or lesser risk of injury, which is what we're after.
Is this where? Oh yeah. One thing that's really interesting is that we often get suggestions from people about, have you considered this risk factor? Is it on your list? And if it isn't, we'll say it isn't currently, we'll run it through the model. And what I've really gotten used to is that the math gives you the answer. You can't just, believe that something must be important or must have an impact. You have to actually see it in the math, which is something that Steve has trained me very well on. So sometimes it's really hard to divorce people of their views of what they have believed to be a very significant, important risk factor. But if it doesn't move the needle at all in the prediction, then we typically don't include it. And maybe you want to say a little more about that.
Oh, absolutely. Well, that's a perfect segue into the model governance. And I know that this morning on the EID discussion, they talked about tweaking the model. And some of us here are like, oh, that'll be pretty easy. You just go and do a little tweakaroo, and it's there. Tweaking models, that's a big, big thing. And I will say it's very difficult to tell your boss, the math says you're wrong. So we've got a way to do that nicely. So when you go and you hear people say, I want to tweak a model, you gotta, and we're talking about the governance now, right? We did the first one, we talked about the data coming in, then we talked a little bit about the details of the model, because I've been asked multiple times, we want to get under the covers. Those were the covers. And now when we take a look at the government piece, this is counting down, anyway, when you get to the governance piece and someone says, hey, I want to adjust the model or I want to tweak the model, you've got 4 things. You can change those equations. That has nothing to do with data. You can just go, you know what, I think LSTM's stupid. I don't ever want to use it. Great, change the equation. You can change the features, which means you can change the data that you gather or the data you're going to include, or you could change the actual feature engineering that you're going to use to create that piece of data. You can change the training set. That's the data that you feed into those maths and those features that actually spits out the prediction on the other side. And a lot of times people talk about their proprietary information when it comes to modeling. The math is never the proprietary information. It's really the training set and your feature engineering. That's where the secret sauce lives. Last one, and then the goal. What are you really after? So this is certainly how we do it at HISA. So I'm not going to say this works for everybody. But we let our subject matter experts, and there's a bunch of them in the back there, who will say, hey, I think we should be doing this, or hey, I think we should be looking at this variable. They'll send it off to the geek squad. They'll do their thing. We'll figure out what it's going to take to implement it. We give that back up to the steering committee. They then look for a strategic alignment, budget, priorities, et cetera, hand it back to the nerds, geeks, and analysts, and then we then start in this sort of development circle with the subject matter experts. One of the things I've found that works incredibly well in this particular type of technology is very small, discrete teams, and at times put them in competition with one another. Like, I don't care what you're going to do, but this is the one who comes up with the best math, data, features that actually do a better job in predicting something. That's the model we're going to go with. So it's not always about, oh, we're all going to sit in a room and hold hands and sing Kumbaya and we're all going to be in agreement. Sometimes you need a little Darwinism in this. So that's a big piece if you're starting to think about, I want to do AI work for company X. This thing scrolling by here at a very fast pace, this is what we use to make decisions. So when someone says, I have an idea and I want to include something in a risk factor, we pump out one of these. And then we sit in a room and you say, hey, look, the math says no. And then they say, oh, no, but it really should matter. And you're like, yeah, well, okay, let me take you through the details. And you take them through the details. And at the end of it, we make a recommendation to the subject matter experts to say, hey, this doesn't move the model, or this has a negative impact on the model, so we highly recommend you don't use it, or it does move the model. So that's that governance piece of you need independent teams, you need to find a way that you can make good decisions, and you got to trust the math. Okay, so how are we doing? So this slide here is what's called the confusion matrix. And it's a great term. Again, my wife says I am a confusion matrix. So that's not a term of endearment. On it, you will see across the top, we have the forecast, and down the left-hand side, you have the actuals. And this is what our model's doing today. We at HISA focus on that bottom corner, which is known as the false negative, where we say that a horse won't have a bad day, and the horse did have a bad day. That's our North Star and guiding light. Because what we don't want to do is say, this horse is good, and then the horse has a bad day. That's our 100% crucial point. You go on the upper side where you take a look at that false negative, you can think of that as the efficiency or the give a heck factor. We cast a pretty wide net because we're really worried about that 5%, and we're gonna have a bunch of missed forecasts on a horse having a bad day. We will, as in, it didn't have a bad day, but we're not gonna miss too many horses that did have a bad day. So, I know that sounds a little circular, but if you think about from our side, and if anyone here is gonna start pushing out or wanting to take a hard look at using machine learning to help predictions, you gotta figure out, do you really give a crap about the false negatives? Do you really give a crap about the false positives? Because it's really tough to have both. Okay, so the little robot here is trying to actually find the 1 in 5,000. So I'm trying to put this into a normal kind of concept, and that is average racetrack, 70 starters. 49, they're not going to have a bad day. 21, they'll have a bad day, meaning not just they died, but they were on a vet's list, had a layup, whatever. We're going to miss 3. But we're going to get 18. So we think that's an important thing to take a look at, to go, hey, look, we can start to say, hey, these are horses that are going to have a bad day. You should probably take a look at it. We shouldn't at least blow it off. But you need people to make that call. This cannot make the call on its own. Just can't, never will. And so the little bottom one here basically says, hey, out of 5,000 horses, unfortunately, there'll be 5 that won't come home. When we take a look at our model, and we've looked at it, is over a year, we will have gotten 4 out of the 5 right. Unfortunately, we will miss 1. But again, I think it starts to say that, hey, maybe this isn't for everyone. Maybe this isn't the panacea. I think that was a great line from earlier this morning. However, what it does tell you is maybe you could use this as part of your information set. So, in 1 minute and 23 seconds, there we are, in 1 minute and 17 seconds, these are the takeaways. On the first one, on our data ingest, we take whatever the people give us, we use machine learning to help sort it out. We use that to do to standardize our code, so ACE is ACE for everybody. We use feature engineering a lot in order to actually separate noise from signal so we have a better chance at the signal. HISA check, 4 models. Point in time, time series, similarity. And on the last one, when you're putting together your governance things, is you got to have multiple teams. This isn't about just getting 3 guys from the IT department and saying, go do something. This is, okay, I need my subject matter experts, I need my geeks and nerds, and I need my executive group to be able to say, yes, pursue this or don't pursue this. Otherwise, you'll have a big spend and you won't actually deliver anything. Listen to the math. Currently, we're sitting at 5% false negatives. We want to get that. We want to get the false negatives down, and then we'll focus on bringing down the false positives. And that is it.
And first of all, thank you so much, Steve. You can see why he's far more equipped to talk about this than I am. I think just one thing to conclude on that's important in terms of the practical implications is that, like Dr. Parkin said, with respect to his model, this is one tool. It's not dispositive. Nobody looks at the risk model and decides that a horse should be scratched or et cetera. But what is, I think, helpful, or we at least are hearing is helpful, is we run our model against every HISA racetrack, every race card, every single day, and we deliver essentially the results to the regulatory vets at all of our racetracks so that they have essentially a tool. When we first started, HISA a few years ago, Dr. Hassan, Dr. Silverman, Dr. Durenberger, they used to actually manually go through the race cards and essentially do their own risk analysis, and that would take about 4 to 5 hours per race card. Now it's done automatically every morning, and obviously with a much more sophisticated model, as fantastic as they are. So we're going to obviously continue to try to refine that tool and continue to find ways to contribute in other ways. But we're happy to answer any questions. Steve is here if anybody wants to ask questions afterwards. I think that's all. Thank you.